You are going to become accustomed, or you may already be accustomed to using this theorem when you are computing the horizontal asymptotes of a rational function. You look at the polynomials on top and bottom and you compare their degrees, and you have three cases, right? Either the degree on bottom is higher, the degree on the top is higher, or they are equal degree. And based on those three cases, you can determine right away whether the function has a horizontal asymptote or not. And you may remember there are two acronyms that are commonly used in high school math courses to help students remember this theorem. And they're commonly pronounced Bobo to Betsy or Bobo Boatin eats DC. And so these, I hope you can see how these sum up the theorem above, where for Bobo to Betsy, if the degree is bigger on bottom, then the asymptote is y equals 0. If the degree is bigger on top, then there is no horizontal asymptote, or the asymptote is undefined. And if the degrees are both equal, you take the leading coefficients, and that tells you what the horizontal asymptote is. But what I care about right now is, why does the theorem work? In other words, how do we prove it? I want to show you the technique for proof by giving you a few examples. So I want to find the horizontal asymptote of this rational function. I have one quadratic over another quadratic. And if you're using the theorem that we just talked about, you may be able to tell already that the horizontal asymptote should be at -3/4. But here's what we do if we want to prove this using limits. And we do need to prove this using limits. When we are evaluating the limit as x approaches infinity, what we're going to do is divide the numerator and denominator by the highest power of x in the denominator. And this is what that looks like. The highest power of x in the denominator is 2. There's an x squared. And so we are going to multiply on top and bottom by 1/x². Now don't forget that you have to distribute, right? You have to distribute that 1/x² over the 2 terms on the top and the 3 terms on the bottom. And this is what that looks like. You get the limit of 5/x² minus 3 over 4 plus 3/x plus 6/x². Why is this cool? Because we can use properties of limits to examine all 5 pieces separately and make a conclusion about what that limit's going to be because of that. The limit as x approaches infinity of 5/x² is literally 0. As x gets very big, 5/x² gets very tiny and it approaches 0. The limit as x approaches infinity of -3 is -3. Like there's no x's, nothing changes. And it's the same with 4. The limit as x approaches infinity of 3/x is 0. Because as x gets very, very big, 3/x gets very, very tiny. And the limit as x approaches infinity of 6/x² is also equal to 0. And that means that overall, this numerator is going to approach -3 as x approaches infinity. This first piece won't matter so much, and the second piece stays -3. The entire denominator will approach or get very close to +4. In other words, this limit is equal to 0 minus 3 on top over 4 plus 0 plus 0. As x goes all the way out to the end of the number line, this limit is literally equal to -3/4. Remember, again, the leading coefficient of 5 minus 3x² is -3, right? You don't take the first coefficient, you have to take the coefficient for the highest degree x. The leading coefficient of 4x² plus 3x plus 6 is 4, and the degrees of the polynomials are equal. And so this result that we got from the limit is the same as the result that we're getting from the theorem. Here's my second example. To find this horizontal asymptote of this rational function, I'm going to do exactly the same thing. Divide top and bottom by the highest power of x. And in this case, that power is going to be 4. And multiply on top and bottom by 1/x⁴. And when I distribute that, what I get is 4/x minus 5/x³ on top, and 1 minus 3/x³ plus 1/x⁴ on the bottom. And again, using all of those wonderful properties of limits, I can see that the top here, overall, as x gets really, really big, I can see that the numerator approaches 0 and the denominator approaches 1. And so this limit is equal to 0 over 1, or 0. And notice that the degree of the denominator polynomial was higher, right? And so according to the theorem, we already knew the horizontal asymptote was going to be y equals 0, or the value of this limit. My final example here is f of x equals 4 minus x to the 5th divided by x to the 4th minus 3x squared plus 9. Again, the highest power of x in the denominator is x to the 4th. The highest power is 4. And so I'm going to multiply on top and bottom by 1 over x to the 4th. And when I distribute, this is what I get. 4 over x to the 4th minus x on top, right? Because x to the 5 divided by x to the 4, that's what I get. And on the bottom, I get 1 minus 3 over x squared plus 9 over x to the 4. Now here's the interesting thing. Think about what happens as x gets very, very large on the top. 4 over x to the 4th like shrinks away to nothing, right? It gets super tiny. But then you minus x, and x is getting bigger and bigger and bigger. So that numerator, in fact, is getting more and more negative. It's getting huge and negative. The numerator is approaching negative infinity. But the denominator, similar to the previous examples, will actually approach positive 1, 1 minus 0 plus 0. And so overall, this limit is going to be minus infinity, which really doesn't exist, right? And so we knew already that the degree of the numerator was higher, and so we knew there wasn't going to be a horizontal asymptote. And in fact, that's what this limit is telling us, that there will not be a horizontal asymptote because this limit does not exist. Now, the overall proof of this theorem looks technical and intimidating, I think, because of the way that you have to write a generic polynomial with all those subscripts and superscripts, but the technique is really just the same. This is how you have to write a generic polynomial. It's a sub n x to the n plus a sub n minus 1 x to the n minus 1, all the way down to the constant coefficient a sub 0. And so with all of this mess, p of x over q of x, we still have to compute the limit as x approaches infinity of this thing. We're still going to follow the same technique. We're going to multiply on top and bottom by 1 over x to the m, the highest power of x in the denominator, or the degree of the denominator, right? And so we have to distribute this, and it's going to get even more gross. We're going to have all of these fractions within fractions. So it's a sub n x to the n over x to the m. Everything, every little term is divided by x to the m. I did a little simplification in the denominator. So b sub m, x to the m, divided by x to the m, all of those x's go away. So b sub m is just hanging out there all by himself. And similarly, almost all of the x's cancel out of this second term, and so I have b sub m minus 1 divided by x to the 1. So I did simplify the denominator some. What I can tell so far out of all of this is that as x gets very, very big, all of these little fractions, b sub m minus 1 over x, b sub 1 over x to the m minus 1, b sub 0 over x to the m, they are all going to get tiny, tiny, tiny. And so the denominator overall is going to get very close to b sub m. But what about the numerator? So it turns out there are going to be 3 cases with what happens to the numerator. If n is smaller than m, and remember that goes with the case of the degree of the numerator being smaller, that means that the entire numerator approaches 0. Every single little term is going to approach 0. And that is going to mean that the limit is going to be equal to 0, which goes with the case that the horizontal asymptote is y equals 0. If n is equal to m, then the entire numerator approaches a sub n. And why is that? It's because in this first term, all of the x's will cancel with each other because n was equal to m. That means the same number of x's on top and bottom. With all of these other terms, though, those x's don't all cancel. There are some left down below. And so that means all of the other little terms go to 0, which means the whole numerator approaches a sub n, which means the overall limit is a sub n over b sub m, which goes with our case of the 2 degrees being equal. And finally, if n is greater than m, which means the degree of the numerator is higher, that means that the numerator gets very big as x approaches positive or negative infinity. Why? Because with this very first term, you notice that there are going to be more copies of x on top than on bottom, right? Because n is higher. And that means that not all of the x's are going to cancel out. There's going to be at least one left on top. And so this first little term is going to grow and grow and grow as x goes to infinity. And so that means that this limit is either positive or negative infinity, which means the limit does not exist, which means there is no horizontal asymptote.